All right, for Algebra 1, we are starting 8.6, exponential growth and decay. So today is day 1. So we have a lot to just go through and talk about first. Okay, so the objectives are to identify the growth rate and the growth factor of an exponential growth or decay function, and write some functions modeling real-life exponential growth and decay. All right, so a lot of it's going to be determining it, looking at the graphs, kind of that first objective today. All right, so let's get started with the definitions. Okay, exponential growth and decay occur when the value of a function has the same percent increase or decrease during each unit of time. Okay, so sometimes we talk about this like in science. You might talk with Mr. Ryder. I don't know if you guys have done this, where you take samples and you spread that, like you're trying to find bacteria and grow bacteria, and you spread it on a petri dish of agar and you see how it grows. Okay, so there's exponential growth there, is how we talk about that. Or if you would buy a brand new car or a brand new camper or something like that, the rate of decrease, okay, there's like kind of an exponential decay in the value of that. Like as soon as you drive off the parking lot with a brand new vehicle, the value decreases tremendously. Okay, so exponential growth and decay. The next point is, this type of growth is difficult to maintain for an extended period of time. Eventually you run out of space or you run out of resources. If we go back to the growth of bacteria, that petri dish is only so big. At some point, the growth is going to, you can't maintain that exponential growth. It's going to run out. It's the same as like when a baby is born. They grow exponentially in the first few years of their life. And now you all as high schoolers are not growing as much. That exponential growth has changed. When you were born, you weighed 6 or 5, 5, 6, 8 pounds, maybe 9 or 10. And now most of you probably weigh 100 pounds or more. Okay, so that exponential part where you're growing really quickly, really fast, has to stop at some point. You can't maintain it forever. So at some point, okay, the conditions necessary to sustain growth cannot be maintained. So that's what that's talking about. Then we have an exponential function and all of the parts here to this exponential function. So we have f of t equals a times the quantity 1 plus r to the power of t. Notice that we're using function notation, and whatever value we're putting here, so this is t, it's the same as our exponent. So sometimes if we use t, we might be talking about time. If we use n, it might be the number of times something happens, or the number of intervals, we might say. If you use d, it could stand for days, like the number of days. So we can change that a little bit depending on what we're talking about. Okay, but then we have a is the initial amount we start with, and r is our growth rate. Okay, so this exponential function is the same for growth and decay. Okay, this is for growth and decay, the function. The only difference is the r value. Okay, so if r is greater than 0, it models exponential growth. If r is between -1 and 0, so if r is greater than -1, but r is less than 0, models exponential decay. Okay, and the last thing there is this quantity, 1 plus r in parentheses, is called our growth factor, and sometimes that's called b, the b value. We won't see that in today's notes, but you might in the future. So there's a lot of information about exponential function. Okay, and we're going to be picking out those pieces in a little bit. So hopefully you've got those down. All right, so let's talk about exponential growth and exponential decay a little bit more. So first of all, exponential growth. Okay, let's look at the left side here. Under ideal conditions, the number of fish in a pond initially stocked with 1,000 fish, okay, initially stocked, that's our initial value. Initial value. So 1,000 would be our A. Okay. Increases by 50%. Okay, so we know it's increase, so it's growth, but it's saying by 50% each year. That's our R value, is 50% or 1/2 or 0.5. However, you can use the fraction or the decimal, but we do have to convert that percent when we're going to do our calculation into something else. So this makes the next year's population is 150%. So this is that growth factor. Okay, so the growth factor, it's that 1 plus R value. Okay, so it's kind of done for us. All right, so then they have a table to show us the population increase here and the population. So in year 0, we had a population of 1,000 and a population of 1,000. So that's what's graphed here, right? Year 0 is 1,000. Let me change the colors here so maybe they'll stick out a little more. Okay, in year 2, we did 1,000 times 1.5. And that gave us 1,500 people. So in year 1, 1,500 people. Okay, in year 2, now we have 1,500 times 1.5. Okay, so that's a little harder to maybe see, like we wouldn't necessarily always fill it out that way, or we can look at it as 1,000 times the quantity 1.5 times 1 times 1.5, which equals 1,000 times the quantity 1.5 times 2. Okay, so here you go. This is the deal. We're going to take that shortcut route, okay, because the year was 2, okay, and so our exponent is also a 2, and that gets us 2,250. So in year 3, if we write this, okay, we've got 1,000 times our growth factor, 1.5, raised to the power of 3. And that gives us 3,375. Okay, so this is exponential growth. You'll notice that the line, right, is increasing rather quickly. All right, so now let's look at the exponential decay example. Okay, so suppose the population decreases by 25%. Okay, so we're decreasing by 25%, so this is decay because it's decreasing. 25% is our R, so R equals a negative 25%, okay, because it is decreasing. Or we would say negative 0.25, because again, it's decreasing. It says after the population reaches 10,000. So 10,000 is our initial, because after 10,000, then we start to decrease. So next year's population will be 75% of the current. So that's that growth factor. When you do 1 plus the R value, in this case it's 1 minus 0.25 equals 0.75. Okay, so that's 75%. But it came from doing 1 minus our rate up there. Okay, so the same thing if we look here in the chart. Year 0, we have 10,000 now, because at this point is when it starts to decay. And then we can't really see the work in the first problem, but in year 2, notice that we have 10,000. Wait, hold on, it's right here. We have 10,000 times 0.75, our growth factor, to the power of 2, because it's year 2. Like year 4, it's the same thing, 10,000 times 0.75 to the power of 4, because it's year 4. Okay, so using that to help us. And you'll notice that then decay, right, our graph is declining. Okay, so as our x gets larger, our y value gets smaller. Yesterday in class we talked about what kind of relationship is this, right? This one is an inverse relationship where exponential growth is a direct relationship, or we could say inverse or indirect. Okay. All right. So for example 1. Example 1 is starting us off really easy. Okay, so for each exponential function, we're identifying the initial amount. So that's our a value, is the initial amount. The growth rate, that's our r value. And the growth factor is that 1 minus r, or 1 plus, pardon me, r value. Then we're supposed to state whether the function models exponential growth or exponential decay. So a and b are stacked on top of each other this time instead of across. So we'll do those first. So when we look at this, we are comparing this to the function that we have above, right? F of t equals a times the quantity 1 plus r to the power of t. So if we're comparing this equation to this one, our a value is what? Good, it's 500. Our r value, notice it's minus 0.75. What's that make our r value? Good, it's a negative 0.75. So then our growth factor, so I'm going to put GF on here. Okay, remember that's the 1 plus r is, so this is 1, it's the 1 minus 0.75, which is equal to what? Good, 0.25 is our growth factor. Excellent. All right, now, so is this modeling growth or decay? All right, it is decay. I'm going to put that as a colon there because our r is less than 0. Okay, our r is less than 0. Okay, let's look at the next one. Okay, so we're going to do b next. What's my a value here? Again, we're comparing it to our function, the function form. Good, a is 100. What's our r value? We're looking at the r inside the parentheses. Perfect, it's a positive 2.5. What's our growth factor value? Remember, that's when we add the two together. 1 plus 2.5 is? Excellent, 3.5. And is this showing growth or decay? Good, this is exponential growth. Okay, because r is greater than 0. It's 2.5, right? Our rate is always going to tell us. Okay, C and D look a little more unusual, okay, because they're not in our exponential function form. So we have to put them in there. Okay, so that means so 2 is the value that's raised to our exponent. So we have to think, what would be inside our exponent, or what would be inside our parentheses to equal 2? 1 plus 1, right? 1 plus 1 would equal 2. Because in the formula, it has a 1 first. So we know it has to be, if I go back and we know it has to be 1 plus our rate. So it has to be 1 plus 1 to equal 2. Okay, and then we need an a value as well. What are we going to put out here that when we multiply it by the number inside the parentheses, we still get 2? Okay, that's also a 1. So now we're looking at the function of d equals 1 times the quantity, 1 plus 1 to the power of d. All right, so now that we have it written in the right form, our initial value is how much? Good, it's 1. What's our rate? Also 1. Good. What's our growth factor? Okay, remember that is equal to the 1 plus r, or in this case 1 plus 1. Good, so it's 2. So does this represent growth or decay? growth, and why? Okay, because r is greater than 0, right? Our r value is 1. Try to switch colors there. There we go. Our r value is 1. Okay, so for D, we're going to have to do a similar thing that we did in C. Okay, because we just have 1/2 x. We need to get this in that form, 1 plus r to the power of x. So we have 10,000 times the quantity 1 plus, what does our r have to be to make it equivalent, to make 1 plus this number equal to 1/2? Good, it has to be a negative 1/2. Because 1 plus negative 1/2 equals 1/2. So if I work this backwards, kind of, 1 plus negative 1/2 is 1/2. So we would end up with the same equation that we had up there. So that's going to be helpful. All right, so for D, what's our initial value? Good, it's 10,000. What's our rate? Excellent, it's negative 1/2. What's our growth factor? Remember, that's that 1 plus r. That's a positive 1/2. Good. So is this one representing growth, exponential growth, or exponential decay? Perfect. This one is decay. Okay, because r is less than 0. It's negative 1/2. Very good. So we're just picking those elements out at the moment. Okay, on the back, example 2. Some of you will, I think, appreciate this example. In a single elimination tournament, half of the teams are eliminated each round. Okay, so this is how you kind of calculate how many rounds it's going to take. It says write an exponential function representing the number of teams left after each round if the tournament begins with 64 teams. B, determine the number of teams left after 3 rounds. And C, graph the function to find how many rounds it takes to determine a champion. Okay, so I've got the table there and the graph for B, but we need to do A and B first. Okay, sorry, those are for C. All right, so write an exponential function representing the number of teams left after each round if the tournament begins with 64 teams. Okay, so if it begins with 64, that's our A value. So let's write, so remember, our form is f of t equals A times the quantity 1 plus r to the power of t. Here, like t would be time. Since we're talking about the number of, or rounds left after each round, we could use r or we could use n. So let's use n, okay, and that's going to equal the number of rounds, like in the tournament. All that means is that instead of saying f of t, I'm going to say f of n, and it's going to be raised to the power of n, number of rounds. Okay, so if we're beginning with 64 teams, okay, so we're beginning with 64 teams, A, our initial value is 64. Okay, then it says, if we go back and read, in a single elimination tournament, half of the teams are eliminated each round. So what's my rate? So one, we have to think, okay, teams are eliminated. So is this growth or decay? It's decay, so it's going to be a negative, and half of the teams. So that's going to be a negative 1/2. Now we're ready to write our function, because it's our function of the number of rounds equals A is 64 times the quantity 1 minus 1/2 to the power of n. That is A right there. That is our exponential function. B then says determine the number of teams left after 3 rounds. Okay, well here our n is equal to 3. Well, all we do is plug 3 in where we see n in our equation. So the function of 3 rounds equals 64 times, what is 1 minus 1/2? Okay, it's a half. That'll make it a little easier. To the power of 3. And you can put that in your calculator. Make sure you put it in correctly, right? It's not 64 times a half and then to the power of 3. It's 1/2 raised to the power of 3. We have to do the exponent first, times 64. And that's going to give us 8. So there are 8 teams left after round 3. There's B. Okay, and now we're ready to start C. So n, we're going to have n here, our n value, and then we're going to do our work for our function, our f of n, so our x and our y or whatever. But don't forget, our initial, with no rounds, we had 64 teams. You can plug that into the formula, or you can just write it like they did on the first one. If we use the formula, however, it would be 64 times 1/2 to the power of 0. And that does equal 64. Okay, but we're just going to check this for each round until we only have one team, right? To determine, we want to determine a champion, so that means we can only have one team left. Okay, so then the next time we're going to have 64 times 1/2 to the power of 1. Well, that equals 32 teams. The next time it's 64 times 1/2 to the power of 2, because our n value is 2. That equals 16 teams. You probably see a pattern here, especially since we already did the work for 3, right? 64 to the 1/2 to the 3rd power equaled 8 teams. I'm sure that you see a pattern emerging, right? Every time half the teams are getting eliminated. So it's going to be 4, and then in round 5 there's going to be 2 teams left, and then in round 6 there's going to be 1 team. We have determined a champion right here. So we don't even need to do 7 and 8. Okay, we don't have to do them because we have a champion. We're not going to have half of a team. Okay, so now we also need to graph this. So graphing this, we need a title. So we might have teams in a tournament. Then we need the teams left, right? Determine the number of teams left. So that's going to be here, the teams left, or the teams remaining. And we had 64 to start with. So do 10, 20, 30, 40, 50, 60, 70 there. That'll get us. So this corner piece is always 0. And then our x-axis is going to be, let's see, after n rounds. Okay, because how many rounds is it going to take? So we need 1, 2, 3, 4, 5, 6 rounds. And then we need to graph our data. So at round 1, or 0, right, because there's a 0 here too. So at round 0, that initial number was 64. After round 1, it was 32. In round 2, it was 16. And then in round 3, it was 8. and then it was 4, and then it was 2, and then it was 1. Okay, so we can see, is this exponential growth or exponential decay? By your graph, right, you should see that it shows exponential decay. Just like here, we should see in the chart, it's showing exponential decay. These are ways of self-checking. We also talked about half the teams are being eliminated. That told us it was decay. So if your table and your graph and your information aren't matching, you know you're wrong. All right, then we have one more problem to do. Okay, in example 3, and unfortunately, you need to cross this stuff about compound interest off. I split this into 2 days, and I didn't get it deleted before I printed it, but I hated to print again and waste paper. So just cross it off, and we're going to show your work for example 3 down here. All right, so example 3, a 5-gram mold culture, that's helpful, increases in size by 200% every day. Write an exponential function modeling this growth, right, growth and increases, and find the size of the culture after 1 week. Okay, so we have to write an exponential function and find the size after 1 week. Okay, so let's think about, first of all, remember in the beginning of notes, we had f of t equals a, the initial value, times the quantity, 1 plus r, raised to the exponent that you have here, if it's t or whatever. Okay, so a is our initial value. What is our initial value of mold here in this example? Excellent, it's the 5 grams. Okay, that is our initial value. How about what is our rate? Our rate of growth or decay. Okay, so it increases, so we should know it's positive, and 200%, that's our rate. So if our rate is 200%, that's cool, but we can't leave it as percent. We have to change it to a decimal. So what is 200% as a decimal? It's just 2. Okay, and that's kind of it, right? We needed a and we needed our r value, although we do need a t to solve for it. This one says time, like t, we use like the initial one that we have at the notes says t. This is talking about 1 week. We can't just put 1 because our rate was by day. So let's use d when we write it. Okay, so d is going to be equal to days. All right, when we solve it. And we're supposed to find it after 1 week. So 1 week is how many days? All right, it's 7 days. So our d is 7. Okay, so let's write the exponential function. We're going to use d instead of t. So f, the function of the number of days, equals the initial value. Whoops, I need to actually write the initial value. What is our initial value? What is our a? It's 5, good. Times the quantity 1 plus, what's our rate? Good, it's 2. Okay, and this is to the power of d. This is part 1 of that. Write the exponential function. Now we need to go back and write it and solve it for when d equals 7. Okay, so we're going to say, all right, well, we're looking for the function of 7 days. So that equals 5 times, what's 1 plus 2? Good, it's 3 to the power of 7. Okay, again, make sure you're solving, doing your exponent first. What's 3 to the power of 7 times 5? So f of 7, you should get, is 10,935. And what is my unit of measurement? Okay, we have to go back to the problem. It is grams, G. All right, so that's it for our first day of exponential growth and decay. Okay, so we will revisit this tomorrow and it'll get more complex. If you are struggling tonight, this video will be up on YouTube. Go back and watch it again and take notes, okay? So that you have that extra practice. Otherwise, you can get started on your homework, page 361. Take that off.